So, discussing the sun, we need to observe the sun. And I'd mentioned before, such as the Dunn Solar Telescope, a lot of these big professional telescopes that study the sun. There's another one called the Big Bear Solar Telescope, and they are specially constructed to do this because you're gathering a lot of energy from the sun. That a huge amount of energy can actually damage things when you concentrate it. And the other thing is that the sun is only visible in the daytime. Well, duh. Okay, so as the sunlight comes in and heats the ground, you heat the ground and warm air rises, and all that turbulence then interferes with the view. And so that's one of the biggest problems with observing the sun. And so the Dunn Solar Telescope or the McMass Solar Telescope, the strategy that they have is to observe the sun where the heliostat is located very, very high off the ground. So hopefully some of this turbulence is dissipated. The other strategy that the Big Bear Solar Observatory uses is to actually have the observatory built in the middle of a lake, so that the cool water around it, when the water doesn't heat up as much as the ground, and so it actually makes the air cooler near the surface, and so instead of air rising, it sinks, and so you don't have that turbulence there. And so that's another strategy. Small amateur telescopes don't have that luxury, but typically the smaller telescopes, the turbulence is less of an issue sometimes because the convection cells are all larger in the telescope. To get away from atmospheric effects, you really want to get out of the atmosphere, and so that's pretty much the strategy here. Now, they suspected as much, though you didn't really have any proof of it. Remember that Lyman Spitzer actually suggested that maybe a space-based telescope would be a really good idea, and he's often credited as the one who came with the idea of the Hubble telescope, but implementation is way before the Hubble, a couple decades before, and that is that if you look at Skylab. Now, Skylab was America's very first space station, and on board was a telescope that the astronauts could point in at different sort of objects. They put a filter on it so that they could point at the sun without it burning out the telescope. And I should point this out: if you do have a telescope or binoculars, do not, under any circumstances, point it at the sun unless you know what you're doing. Julie knew exactly what she was doing, very accomplished amateur astronomer, and so she was capable of putting a filter on her telescope that blocked out 99.9999% of the light, and put a camera on it to record what she was seeing. Don't do that yourself unless you know what you're doing, because looking at the sun can be exceedingly dangerous. But Skylab had after they were trained to use the telescope, they weren't actually looking in the telescope, but they would point it and take pictures. And they had other instruments. So remember, we don't just look and take pictures. Astronomers have instruments that we use to study the sun. And so they were able to find that they were able to make measurements of the sun that showed the different parts of the sun were moving differently than other parts, something that a little bit surprising for them. They also found that the spectrum of the sun changed in a little bit of ways that they weren't expecting over the course of the time that the Skylab was up there, which really wasn't all that long. And they also discovered in just that short amount of time that the total energy output of the sun varied over time. In fact, there's a term called the solar constant that is supposed to represent the energy per time per unit area coming from the sun. And they realized the solar constant wasn't constant. No one knew that on the ground because the atmosphere distorts the energy coming from the sun all the time. So solar panels, for example, can be less effective on the ground than they are in space. And on the ground in part because of clouds and haze and everything else. The other So what the Skylab did was prove that the space-based instruments are really a lot better than ground-based. And so not long after, they launched a special satellite called Solar Max satellite, Solar Maximum Mission, but they just abbreviate it normally Solar Max. And the idea was that we knew that the sun went through cycles of activity. You know, a lot of activity, little activity, a lot of activity, little activity. And so they were going to launch it so that it measured over the solar max. And so a complete cycle of the sun lasts for about 11 years. So this had a decade or so. It's supposed to watch the sun peaking on solar max. And so that was the idea. And of course, we learned a lot about the sun, but then they realized there's even more to learn. The problem that they faced was that when Earth looks at the sun, then always, every time Earth is looking at the sun, you're looking from Earth. Earth orbits the sun very close to the sun's equator. And so that means that no matter where you are on Earth's orbit looking at the sun, you're looking at the sun's equator. And so the question is, does the sun look different from a different angle? And so you wanted to put a satellite where it could look down at the north or south pole of the sun. Now the problem is, when you launch a satellite from Earth, it's going around the sun with Earth. Okay, and so it's in the same orbit. And so you want to somehow figure out, well, how do you get a satellite, not into this orbit, but into that orbit? Okay, well, it turns out that's very difficult to do, and involved a rocket that was bigger than we had available. So they cheated. So this was actually something the European Space Agency did. What they did was they launched the spacecraft not directly to Jupiter, but they launched the spacecraft instead. They launched the spacecraft out to Jupiter, or rather, they launched it, instead of launching it directly to the sun, they launched the spacecraft instead of directly to the sun, they launched the spacecraft to Jupiter. And then Jupiter's huge gravity grabbed the spacecraft and tossed it into an orbit that was running perpendicular to the plane of the planets. And so that way it was able to look down at the north and south pole of the sun. And so it's got an orbit that takes several years, and it made 3 orbits before it died, and was able to look at the north and south pole of the sun. And so this was the first look at the pole of the sun, and we'll talk more about how that works later. Other spacecraft that were launched here, the SOHO spacecraft, Solar and Hemispheric Observatory, Solar and Hemispheric Observatory. It is designed to, it's again a European Space Agency mission designed to measure the sun, and it's orbiting out here on Earth. It's not actually going close to the sun, but it's orbiting, keeping track of the sun. And then the A spacecraft, Advanced Composite Explorer, and it was actually launched to a spot that's between the Earth and the sun, so that the Earth's gravity pulls on it, the sun's gravity pulls on it, and it stays in that spot between Earth and the sun. Now, the advantage there is, and having other satellites that are at that location, is they act as early warning satellites. When something's happening on the sun, it's going to hit those satellites before it hits Earth. We'll talk more about that, why that's important later. One issue with the sun is you're always looking at the sun with just a picture, a flat image, but the sun's not really flat. It's actually got 3-dimensional structure to it. You've got things that stick up off the surface. And so NASA launched these 2 spacecraft called Stereo 1 and 2. And so the 2 spacecraft were able to look at the sun from different angles. So the idea was you launch it from Earth, one's in an orbit that's a little tiny bit closer to the sun than the Earth, one's a little bit further out, so that means it runs a bit slower, so that means one gets further ahead, one lags behind Earth, and so they're able to look at the sun from different angles, and therefore you get a 3-dimensional picture of the sun. Well, that worked just fine after they launched it until, and then the 2012, 13, 14 thereabouts. Really interesting thing, they were kind of on the other side of the sun, and so we could actually see the far side of the sun while we're looking at the near side of the sun here. So we have the 360 degrees of the sun. But in 2015, they were directly on the other side of the sun, and so the energy from the sun was blocking our radio signals. By 2016, we were getting signals again. 2018, and then into 2020, they're now separating here so that the A and the B here, they're now looking. This one sees that part of the sun. This one sees that part of the sun, and so there's actually a gap on the far side of the sun now where we can't see what's happening anymore. And so for the next number of years, these things are going to be getting closer and closer to each other here, and we're not going to have this. We're not going to have the images of the far side of the sun. See what's about to be rotating into view towards us, and that's important because sometimes you have an active region on the sun. If that active region rotates towards us, we want to be aware it might throw something at us. Latest mission to the sun was actually the Parker Solar Probe, was launched just a couple years ago, and it was actually going to fly close to the sun. So it actually flew by Venus, so Venus's gravity throw it towards the sun. And 2018, it made its close approach to the sun. Perihelion, if you remember when we talk about Earth's orbit around the sun, perihelion is the closest to the sun. So if you have an orbit, then an elliptical orbit, perihelion is the closest to the sun. And so it reached perihelion. It's going to keep making these orbits until 2025. Last couple of years of its mission, it'll be making its absolute closest approaches. In fact, it's gonna be going so close to the sun, it's gonna dip into the outermost parts of the sun, the corona. And so we're getting our first very close views of the sun. It's got a special heat shield on it here to protect it from the sun. Has solar panels that powers it, but it folds up the solar panels behind the heat shield when it gets close to the sun, so that the sunlight doesn't damage the sun. In February of this year, in fact, turns out the European Space Agency launched another one to the sun, and that's the Solar Orbiter. And it's going to actually, it was launched, so it's going to be, again, tossed into an orbit closer to the sun than Mercury, but with a very, very high inclination. That means it's tilted relative to the orbits of the planets, and so it's going to see the polar regions. In fact, it's expected to get a better view of the polar regions even than Ulysses, because it's going to be a lot closer. And so we're going to get a second look at the polar regions, verify some of the stuff at Ulysses. And again, Ulysses was done a long time ago, almost 2 decades ago. And so you can imagine the amount of technology that's changed since then, so how much better of a view this thing could possibly get.